Welcome to class, everyone. Today's explainer is all about breaking down one of the absolute most critical engineering challenges we face in modern power systems. We're talking about reactive power control and how to maximize power transfer in AC grids. So grab your notes and put on your engineering hats because we're going to dive deep into the math and physics that literally keep our modern electrical infrastructure up and running.
So here's the big question. How on earth do we push maximum power through a wire without just breaking the grid? It sounds something, right? But this is the fundamental high-stakes problem of transmission engineering. We have to transmit massive amounts of power over huge geographical distances, and we have to do it without suffering a catastrophic loss of voltage control. It's an extreme balancing act, folks. If we get the math wrong here, the whole system collapses. All right, here is our roadmap for today. First, we'll cover the AC transmission challenge. Second, the limits of uncompensated lines. Third, fixing things with passive compensation. Fourth, enter the StatCom. Fifth, series compensation with the SSSC. And finally, number 6, the future of power flow.
Okay, let's jump right into Section 1, the AC transmission challenge, and establishing our baseline.
Moving to slide 5, take a close look at this figure right here. We're assuming the sending end is connected to a generator providing voltage Vs, and the receiving end gives us voltage Vr to a load. Now, you know a transmission line isn't just a simple piece of wire. We actually model it with distributed parameters across its entire length. If you follow my pointer down to the equations below the circuit, you'll see exactly what I mean. We've got our series resistance R, series inductance L, shunt conductance G, and shunt capacitance C. By analyzing just a tiny little slice of the line, let's call it dx, we can derive these differential equations. And these equations tell us exactly how the voltage and current are going to behave and shifting phase as they travel over hundreds of kilometers.
Now on slide 6, follow my pointer to this really beautiful theoretical state we call surge impedance loading, or SIL. Imagine a completely lossless line. The surge impedance, which we often denote as Z sub n, is the square root of the line's inductance divided by its capacitance. Now, when the load we attach perfectly matches this surge impedance, something basically magical happens in the math. The power transfer perfectly balances out. The reactive power generated by the line's capacitance is exactly consumed by the line's inductance. So the line is essentially supplying its own reactive power. The result? The voltage stays perfectly flat across the entire distance of the line.
But, of course, things are rarely that perfect. Let's move to Section 2, the limits of uncompensated lines, or what I like to call the messy reality. On slide 8, we see that raw, uncompensated lines actually face 2 massive limitations. First up, look at point number 1. When we have heavy industrial and commercial loads that exceed that SIL we just talked about, the line's inductance absorbs way more reactive power than the capacitance can generate. The result? The voltage completely sags and we risk a total blackout. Now check out point 2. At the opposite extreme, say it's the middle of the night, hardly any load on the system, the line's capacitance absolutely dominates. This creates excess reactive power, which causes the receiving end voltage to actually spike even higher than the sending end voltage. We call this dangerous overvoltage condition the Ferranti effect. To see this visually, let's look at slide 9. This figure illustrates the problem mathematically. Following my pointer here, the x-axis represents the length of the transmission line, and the y-axis is our voltage magnitude. See that perfectly flat line right in the middle? That is our ideal SIL condition, where power equals P sub n. But look what happens during heavy loading. Notice that dramatic sag in the bottom curve, where P is greater than P sub n? The voltage drops severely right at the midpoint, Vm. Now, flip that around. Look at the top curve during light loading, where P is less than P sub n. We get this massive, dangerous bulge of overvoltage peaking right in the middle of the line. If we don't manage this, it'll literally destroy grid equipment. So how do we handle this? Let's get into Section 3, fixing with passive compensation, where capacitors and inductors come to the rescue. Right here on slide 11, let's compare the raw equivalent circuit to a compensated one. On the left side, we have the exact pi equivalent circuit of your standard uncompensated line. But on the right, look at what we've added right at the midpoint. We strategically inject a series capacitor, you can see it labeled with a reactance of negative Jx sub c. We also throw in some shunt reactors, which are inductors connected to ground on either side. By physically inserting these passive components into the circuit, we're basically artificially counteracting the line's natural properties. We are manipulating the phase constant and the characteristic impedance entirely to our advantage. Moving to slide 12, it is absolutely crucial to understand the distinct roles these different components play.
Bottom lining the math from our derivation notes here. Series capacitors act like a supercharger for active power flow. By canceling out the line's natural series inductance, they effectively shorten the electrical length of the line, which massively increases our power transfer limit. Shunt devices, on the other hand, well, they're the heavy brakes. Inductive shunt reactors are an absolute necessity to absorb that excess reactive power and stop that dangerous Ferranti overvoltage when the line isn't carrying much load.
Passive components are great, for sure, but they're static. Let's look at Section 4. Enter the STATCOM, where we introduce active, solid-state control.
Turning to slide 14, let's check out this new circuit and see how it builds on what we just learned. Here, placed optimally right at the midpoint of the line, we have our STATCOM. Now, unlike a passive capacitor, the STATCOM acts as a highly controlled constant reactive current source. You can see it represented right here by I sub R. It uses solid-state power electronics to actively monitor the line voltage, V sub M. If the voltage starts to dip, boom, it instantly injects capacitive reactive current. If it spikes, it absorbs inductive reactive current. It's this incredibly dynamic sub-cycle response that keeps the midpoint voltage totally rock solid.
Now on slide 15, the engineering proof for why this matters so much is right here in this power angle curve. Follow my pointer along the x-axis, which is our power angle, delta, and the y-axis, the normalized power flow. The lower curve shows the maximum power limit for an uncompensated line. But check out that higher arc. That clearly demonstrates how a STATCOM, by injecting optimal reactive current, vastly increases our maximum power transfer envelope compared to just a naked line. We get significantly more power pushing through the exact same physical wires.
Moving to slide 16. Listen up, class. If you take away just one number from these standard derivations today, make it 90 degrees. In our standard AC transmission equations, maximum power transfer occurs right when the power angle hits 90 degrees. Now, a STATCOM's dynamic nature can actually push that absolute maximum power threshold to an angle somewhere between 90 and 180 degrees, depending on the current injected. But 90 degrees remains the absolute optimal power angle benchmark where maximum theoretical power transfer fundamentally aligns with this active shunt controller in our standard derivations. It really is the critical tipping point for grid stability.
Next up, Section 5, series compensation with the SSCC, which is our active series solution.
On slide 18, take a look at this equivalent circuit. The static synchronous series compensator, or SSSC for short, is fundamentally different from the STATCOM. Instead of injecting current down to ground in parallel, the SSSC injects a highly controlled reactive voltage, labeled VR right here, directly in series with the line current. By varying the magnitude of this injected voltage, the SSSC can smoothly and continuously shrink or expand the line's effective electrical reactance. It's honestly like having a dial in a control room that lets you just change the physical length of a transmission line on the fly. Continuing to slide 19, when we do a mathematical comparison of these two power electronic giants, an incredible advantage emerges. To achieve the exact same level of power transfer enhancement on a given line, the SSSC actually requires a significantly lower megavolt ampere, or MVA, rating than the STATCOM. Why? Because the SSSC operates directly on the series impedance, rather than just supporting the voltage via shunt current. It's a vastly more efficient use of silicon and capital for the specific goal of pushing more active power. On slide 20, let's take a look at this real-world load curve. Using my pointer here, the horizontal axis is normalized power, P, and the vertical axis is our normalized load voltage, V. This is often called a PV curve, or a nose curve. Curve I right here represents our uncompensated line. Notice how, as power demand increases to the right, the voltage rapidly collapses towards the tip of the nose. It just drops off. Now look at curve Tri. That represents applying ideal dynamic compensation. See how it dramatically pushes our absolute power limit way out to the right? This allows the grid to serve massively higher loads without suffering that catastrophic voltage collapse. Finally, Section 6, the future of power flow, and how we adapt all this to modern grids. On slide 22, let's wrap up our main takeaways from today's explainer. The biggest lesson? Pushing maximum power is always a delicate balancing act that is strictly constrained by physics. Power flow is ultimately bounded by voltage stability. Passive devices are our foundation. They're cheap, they're effective, but they are totally static. Dynamic FACS controllers like the STATCOM and SSSC, well, they are the master key to maximizing grid capacity. But remember, they aren't magic. As our equations show today, engineers have to constantly and carefully manage the real risks of electrical resonance and fault transients when implementing them. And finally, on slide 23, I want to leave you with a pretty provocative thought to ponder before our next session. We built all these mathematical models based on traditional, highly predictable generators, but as unpredictable wind and solar energy begin to completely dominate our grid, causing rapid second-by-second fluctuations in power flow, how are we going to adapt? These active solid-state controllers won't just be a helpful little efficiency boost anymore. They are going to be the absolute only thing holding the entire electrical system together. Keep that in mind. Thank you so much for joining me in class today, and I'll see you next time.